So it's a great pleasure to introduce Himanshu Grover. So Himanshu got his PhD last year from Pittsburgh University in biomedical informatics, and then joined my lab about a year ago. And now he's working out different methods to utilize the large amount of public proteomic data that's available. But it's available, but it's rather difficult to access and difficult to reanalyze. So what he's working on a framework where he would collect data and make it easily accessible, and we'll talk about that a lot. And the other reason why this is especially important in proteomics is that in genomics there are quite well-developed methods, and one can define the sequences from the raw data. But in proteomics, our methods are still improving a lot, and a large part of the mass spectrometry-based proteomics data is not yet understood. So there are probably modifications that we don't know about and other kinds of things. So it's therefore very important to have a large collection of all the data to be able to explore these things and use it to improve methods. Okay, thanks.
So you just described. So I'll be talking about the framework that we've been working on for the last few months to store, manage, analyze massive amounts of proteomic data. Okay. So just a brief background. I'll first start with a brief background on mass spectrometry, just describe what kinds of data we have, what we are trying to store out of those, why we are storing it, how we are storing it, and how we are trying to analyze it. So that's a straight, simple outline. So starting with mass spectrometry. So this is an analytical tool or a technology that's used to identify, characterize complex mixtures of unknown compounds. It's sort of the mainstay of modern proteomics research, and the schematic shows a very simple picture, or it describes the principle that mass spectrometry uses in very simple terms. So we start with a sample, which is right there, that we wish to characterize. So the first step is to deposit some charge on the compounds in the sample. So that's done by the ionization section. Then we move these ionized molecules into a mass analyzer, which is sort of like a time-of-flight tube fitted with electromagnetic fields. So all these charged molecules fly through it, and naturally heavier molecules will travel slower. Higher charge states will travel faster. And based on the time of flight, the detector sitting at the end will create a spectrum out of whatever reaches there, and so which looks something like this. So on the x-axis, we have the mass-to-charge ratio of whatever molecule was observed. On the y-axis, we have the abundance information for that particular molecule. So that's a very simple picture about how mass spectrometry works. Now, when it applies to proteomics, usually protein molecules are quite bulky, and it's not very straightforward to analyze data that comes out of all mass spectrometry applied on intact proteins. So the approach, the preferred approach is typically, it works this way. So we start with a complex mixture of proteins. We digest the proteins into small peptides using some enzyme digestion like trypsin. And then we have this first stage of mass spectrometry, which basically scans for intact peptides, those amino acid sequences. Based on what we have here, it will isolate the most abundant peaks, and then it will shoot them through another stage of mass spectrometry and generate fragment ion spectra. Okay? Now, for each of these fragment ion spectra, we can go back and identify what peptides generated them. There are several methods to do that. And from that data, we assemble what proteins are present in the sample, and we can also quantify it. So it's a very sensitive and a high throughput technology. We can do identification of proteins in the sample. We can do quantification of proteins in the sample. We can also do differential expression and biomarker discovery between disease and healthy status. So it's quite cool. So once we collect all these fragment ion spectra, this is the level that I'm working at, so I'm working at this particular level, all the fragment ion spectra. So once we collect all these spectra, there are several pieces of information here that we would like to store. So first is just a unique identifier, what experiment the sample came from, what particular file name the experiment came from. Then we have some peptide information from the experiment too. Right now we don't know the exact sequence, but we have some information about it, the mass to charge that the peptide has. And we also have a bunch of peaks. These are basically just MZ intensity values, and they correspond to all these different peaks that we observe in the spectrum. Okay, so that's an important piece of information. Now, the next step is to identify what peptides generated the spectrum. So there are several algorithms, again, which do this kind of work. And the basic idea is that you evaluate each spectrum against several candidate peptide sequences. Okay, so let's assume that this is one candidate peptide that we want to evaluate. So we have some general idea about how these peptides fragment. Okay, so we create a theoretical spectrum for these peptides, and we can compute the mass to charge ratios of various fragments that these peptides can generate. Okay, so those are all blues and reds. Those are all the mass to charge ratios of theoretical fragments. So then we compare these theoretical fragments with the actual observed spectrum, and we can annotate which fragments were observed and with what intensities. Okay. So just to give you an example, this particular fragment corresponds to Y6, which has a mass to charge of 762, and it's observed here with a very high intensity. Okay, so that's the general idea. So now once we have this match between a peptide and spectrum, we get more pieces of important information. So we have more information about the peptide. So we have the amino acid sequence, charge state, mass to charge, theoretical. What error this peptide had in mass to charge terms, what modifications it had, some information about the matching peaks, which fragment ions got matched with what intensities, and some other characteristics. And finally, we have some match statistics. So you use some scoring algorithm to evaluate these different candidate peptides. Those algorithms generate scores, expectation values, how confident those algorithms are in identifying the peptide sequence, so on and so forth. So those are other important pieces of information. So now the question is, why store all of this data? There are several reasons. So even before starting the experiment, biomedical researchers may have questions about what proteins to expect in the sample, or what abundances should those proteins be at, or how do those abundances change with different conditions? What has been basically observed in the past? So those are important questions. We also have important informatics methods research that can basically feed off this data. So what are some of the peptide-specific changes that lead to different peak intensity patterns in the spectra? What are most abundant peaks that are observed for different kinds of peptides? Common modifications and what is their effect on the fragmentation spectra? Are these spectra reproducible or not? And different experimental modalities. So if you fragment peptides based on high energy versus low energy collision or electron transfer dissociations, they all generate different kinds of spectra. So you need to understand their characteristics to build informatics methods around them. Okay. Now, given that we want to store these data, there are a couple of important questions to consider. One is that modern mass spectrometers generate vast amounts of data in a very high throughput fashion. So just to give you an example, a single experiment can generate 10 to 50,000 spectra, sometimes even 100,000 spectra in an hour or 2 hours maybe. When you do peptide identification, roughly 30 to 40% of them get assigned confidently with peptides. So we have that extra information for 30 to 40% of those spectra. And any moderate-sized lab can generate several gigabytes of data per day. And if you scale that to thousands of experiments, you can easily generate several terabytes of data in a month. Okay, so that's quite a large amount of data. Secondly, we saw complex data structures. I showed you some examples what kind of information we care about, but that information has rich structure in it. Okay, so there are some hierarchies. There are some lists and arrays of things that we store. We store a list of peaks. We store a list of identifications. So data structure has complex and rich format. Okay, and also we don't just want our data to sit and rot. We want to interact with it. We want to analyze it and see what it throws at us, okay? So in order to utilize these large amounts of data effectively, efficiently, we have two choices. Either store all these thousands of files in file system directly. So we can store them as ASCII files, text files, semi-structured formats like XML, binary formats. They are all popular formats. But the problem with these formats is that there's a lot of overhead in parsing these files. If you have like many thousands and thousands of files and you want to extract information out of them, you need to, every time you run an application or an algorithm, you need to read and parse through it. There are no indexing or searching capabilities or filtering capabilities. You need to load all the data and then decide whether you want to use it or not. So that's another challenge. And these are generally just too large to fit in memory, like all these thousands of files. You need to use them piecemeal, which is not good. So the obvious choice is databases, using databases, which allow for efficient storage and access. And they also have several built-in analytics tools, which can reduce the burden of developing novel applications and speed up the analytics part. Okay, so in terms of databases, for the past 2 or 3 decades, relational databases were the only choice, dominant choice that we had. And for all this complex information that I showed in the background, basically relational databases will break everything down into flat tables. So we'll have a peptide table, we'll have a spectrum table, we'll have a match table. So peptide table will store all the information about peptides. This will store all the information about the spectrum files. And match table will have all the fragment ion matches and other characteristics. Now, there are 2 problems with this kind of approach. One is called impedance mismatch. So we saw that there was rich structure in all our data, right? So we had like list of theoretical fragments, list of observed peaks. So there are lists and dictionaries of things, okay? So that's one thing. Different peptides can have different lengths. They can have different number of theoretical fragments. Different spectra can have different number of peaks. So there's non-uniform data, right? So if you put everything in tables, you need to predetermine or predefine how many columns you want. Storing non-uniform data, you need to do awkward things with relational databases. The other thing is that we had complex data structures, so embedded data structures. So let's say mass to charge ratio and mass to charge error. So we had 2 different kinds of errors. We had Dalton scale, we had parts per million scale. Similarly, we had peaks. Peaks is a list of observed peaks, but each element in that list is a further sort of embedded kind of a structure. It had an MZ value and an intensity value. So in order to store all these complex kinds of things in these tables, you need to do, again, awkward things. You need to break them down into different tables, break them down into different columns. So basically, all the data structures that you have in your application code, lists, dictionaries, embedded objects, you need to flatten everything out and store in tables. So that's not good. Also, because it breaks it down into these rows and different tables, you cannot separate them out from one another on 2 different nodes in a cluster, okay? Because when you want to do analytics on top of it, you will have to pull together data from all different tables. That's called a join. And joins are they're a complex operation on large data sets. If you spread it on a cluster, that becomes even more slow and expensive to do, okay? So recently, the last decade or so, many NoSQL, not only SQL or non-relational databases have come into play because of the upsurge of data that's being collected, scientific data, climate, weather data, web data, all these large, massive data sets, social networks. So all these different technologies have been developed to handle data at that scale, several terabytes of data, several petabytes of data. Okay, so they all have a couple of key features. One is that they have this sort of aggregate orientation. Okay, so we saw in the previous slide that all that complex piece of information, that match between a peptide and a spectrum, which we would like to use as a unit of interaction, relational databases break them down into different tables, different rows, right? But what we want is we want them to be accessed as a unit. And that's what is called an aggregate. So all the closely related data that we access as a unit, okay? This also allows you to store rich data formats if you have this kind of representation. So all these NoSQL databases allow you to store rich structure in them. Okay? It simplifies the access, data access, and because of that, the application development productivity also improves, because for most of these complex data structures, you have some representation in programming languages as well. For example, Python has dictionaries, Java has hash maps, so you can directly dump your objects, in-memory objects, into your databases. So that improves or makes it more efficient to access the data. Okay, and these aggregates are these are basically context specific. You need to know beforehand what data would be accessed as a unit. So in our case, peptide and a spectrum match is one unit of information. All that giant document that I showed, that's a unit of information that we would like to access together. Okay. Now there are several different NoSQL databases, which I don't think I have the time to talk about each of those. So there are key value stores, there are column family stores, there are document-oriented stores, and graph databases. They all have different capabilities, different data models to represent data in them. The one that I have been using is MongoDB, which is a document-oriented store. So I'll probably just go directly to that in a bit. So the reason why I chose document, I'll talk about several reasons, but when you compare these different kinds of NoSQL stores, document stores are the one which offer you the maximum amount of flexibility in terms of storage. Very simple, intuitive data model. I'll show how it looks. And the query and analytics also. So the other stores have very limited capabilities in terms of how you can query and access the data, what kinds of analytics you can run on top of it. Okay? So those are the things. So the other important feature of all these NoSQL databases are that they are designed to run on clusters. And that, again, follows from this aggregate orientation. In relational databases, there is no way for a database to know that all these different rows and columns are going to be accessed together as a unit. So if you put all of those on different nodes, then when you query, the query will have to do a join across multiple machines, across multiple tables, which will be a very expensive operation. Okay, so that's why relational databases are difficult to run on clusters. Whereas in NoSQL databases, this aggregate, this idea of aggregate allows you to just dump these different aggregates in different nodes, because we know that this is what our level of data access would be as a unit. Okay, and it supports all different kinds of distribution, replication of data for doing backups and for read-intensive loads. It also does sharding, where you distribute, you break the data down into different chunks, non-overlapping chunks, and you put them on different nodes. You could mix and match replication and sharding, so you can do all kinds of things with it. Okay, so let's go to why MongoDB is what we chose. Okay, so first of all, it's very flexible. So just like in relational databases, you have tables of rows and columns. In MongoDB, you have collections of documents. Okay, these documents are a set of key value pairs, and like I said, most programming languages have some sort of representation natively for representing these documents. This is how an abstract document would look like. So we have a bunch of keys and a bunch of values corresponding to them. These keys and values could be simple objects, just a key and a value, or they could be more complex objects. For example, here for key 3, the value is another subdocument which has a pair of keys and values. For example, this error has 2 different keys in Dalton scale and parts per million scale, 2 different values. Okay? Or it could be a list of things. For example, in this, key 4 has a value which is a list of key value pairs. For example, we had to store all the peaks for a spectrum. We can store peaks as a list of sub-peaks or documents.
Just nitpicking, but wouldn't a graph structure database serve your purpose better, like Neo4j? Because you mentioned in the beginning the data itself is hierarchical.
Graph databases are not necessarily hierarchical. They are meant to capture graphical relationships like social networks. That's not hierarchical. So they are meant to capture complex interactions. Okay. So Okay, so the next reason why MongoDB is a very good choice is that it has a very powerful query language. Okay, so find is the basic query tool that you can use, and this can take as input a query document, and just like you represent data as documents, hierarchical key-value pairs, you can also provide a query in the form of a hierarchical key-value pair. For example, here I'm asking my collection to find me all the amino acid sequences, all the documents which have the amino acid sequence A, C, D, E, G, F, M, P, R, which have a charge state of 2 and which have a parts per million error less than 5. Okay? So we can have simple exact match queries, or we could have more complex operations like inequalities or range queries or regular expression queries over peptide sequences or text. So we can do many complex kinds of queries. Also, you may not want to use the entire document in your operation. You may want to filter to specific parts of the document, so you can actually tell which parts to retrieve after the query. Okay? Another thing, so MongoDB understands all these different hierarchical embedded structures. So here, for example, this MS-MZ error was a subdocument which had 2 key-value pairs. So here we use this dot notation to extract a specific piece out of that subdocument, which was like stored as a hierarchical object. Okay? So it understands all these different nested documents and objects. You can index them, query them fast, and do all kinds of things with it. Okay? The next advantage of MongoDB, this actually applies to all NoSQL databases, that they all have a scale-out architecture, both in terms of storage and processing. So for the current proof of concept study, I have used like 5 commodity machines, standard desktop machines, a total of 28 cores, 36 gigabytes of RAM, 3 terabytes of hard disk space. I've used about 4,000 Spectrum files, which gave me about 30 million raw MSMS spectra. And since the identification rate is about 30 to 40%, I have roughly about 10 million peptide spectrum matches out of those. And this amounts to about 300 gigabytes of data, which is distributed across these 5 different machines. And the benefit is that in my application code, I just need to interact with the main server. It's the job of the server to distribute my data. It's the job of the server to distribute my queries seamlessly. I don't have to worry about distributing any of those things. So all my interaction is with just one server. You don't even know whether. Sure.
Can you explain the concept of what you said earlier about the aggregation of the data with your previous example?
Okay. This one? Okay. So aggregation is this entire document. Okay? In the previous example, I showed that you will have peptide information, you will have spectrum information, you will have the match information, which peaks matched, which did not match, and all those characteristics, right? So in relational databases, all those pieces of information will go in different tables, in different columns, and different rows, basically. Whereas here, everything is stored as a single document. You don't have to do a complex join across different tables. So it's sort of an aggregate unit. Okay? So you can just do one simple query and pull out the entire set of information at once.
So instead of being an array that references other arrays, is a dictionary that references other dictionaries? Like, is that the main difference?
It's not an array referencing.
Because I don't know anything about MySQL, that's why I'm asking.
So basically, in MySQL or other relational databases, there is a concept of a join. Okay, so every table will have one primary key column, but if this data is related to some other data which is sitting in another table, this primary key will be, or some other form of it will be stored in that table as a foreign key. Okay, so when you want to join these two data sets, you will use the primary key here and the foreign key here to sort of collect all the data. So it has to basically combine information from multiple tables. Whereas here, you store this information as a unit. You don't store it in separate dictionaries referencing different dictionaries. You store it in one key value pair. So you have this unique ID.
It's like a series of embedded dictionaries.
Yes, so you have this unique identifier. This is what you need to query in order to get all the information about your peptide spectrum match. You don't have to go to different tables to extract the information. Does that make any sense?
Himanshu, is there any overhead if you have a storage structure like this? Does it have substantial memory requirements, or say you have several such aggregates? I mean, in a relational database, you would just perform the join and then get rid of it. It's just buffered and then you get rid of it. However, here you're actually saving the aggregates. So, I mean, is it kind of inflexible and there's a lot of memory overhead? Or?
So there's no memory overhead right now. So it's relatively a newer database. So there are some limitations to it. So one biggest limitation is that this document cannot be more than 16 megabytes in size. So it has to have. So they're planning on increasing it to 64 megabytes. But I mean, their idea is that if it's more than 16 megabytes, that means your database design is there's something wrong with it. You need to revisit that. So there are some limitations right now, but not in terms of querying or analytics access. So in fact, these are like, these work pretty fast. These are very efficient in terms of how they retrieve and store data. Okay. Okay, so that we've taken care of. Okay, so this, again, I'm just repeating the information I had earlier. So I have one main collection of documents where each document represents one spectrum. So I have some identifier information, some precursor peptide information, and a bunch of peaks. This is my entire spectrum. Then I have a different collection of documents in which I store information about the peptides, about what fragment ion matches were observed, and what modifications were observed, and things like that. So this is my second major collection. Okay. Next reason why Mongo is a pretty good database for this kind of work is the analytics part. So we don't just want to query and retrieve the data, we want to crunch it, we want to do something with it, okay? So Mongo provides a couple of powerful tools for doing analytics. One is called the Aggregation framework, the other one is called MapReduce. I'll, I think, straight away give examples because that's the easiest. So let's say we are interested in finding the top 5 most commonly observed peptides and list their count, that means how many times they were observed, average e-value. E-value is the confidence score that was assigned to the identification, and also compute the average precursor mass to charge error. Okay, so that's our operation. Okay, so we can break this operation down into several steps. So first is we extract the relevant pieces of information. So we want the peptide sequence, we want the e-value, and we also want the error. We group all these according to amino acid sequence because we want to compute the count and we want to compute the average for every peptide sequence. So we group them according to the amino acid sequence of the peptide. Then we sort according to the counts in descending order and limit the results to top 5. Okay, so that's the basic set of operations that you would require to do this query. So when you represent it in Mongo, this is how it looks. So you give the collection name that you are interested in. So this is my match archive. This has about 10 million documents, each corresponding to a peptide spectrum match. So aggregate is the command that you would use. The first step is to extract the relevant pieces of information. There is a $project operator. So we can extract amino acid sequence. We can extract e-values. We can extract the errors out of it. The next step is to group them according to the amino acid sequence, increment the count by 1 every time we observe the sequence, and compute the average e-value and average error at the end. So that's the group and aggregate. And then we sort and limit according to the count, limited to 5. So now imagine if you want to do this operation. It's a very simple operation, but if you want to do this over, let's say, many hundreds of thousands of files, and you want to distribute your workload across many computers, how much work you would have to do? So definitely not one line of code. It would require a significant amount of coding to do this kind of thing. Okay, so you can basically set up a pipeline of operations. There are several different operators. These operators are very flexible and can do lots of things. And you can use these operators as many times in any order that suits your query. Okay, so that's the aggregation framework. Now, this top 5 query is pretty common, not necessarily this particular query, but top 5 in other aspects. Okay, so there is another concept called pre-aggregation. This also exists in relational databases, like you pre-compute something and store it back in the database and keep updating it as you see more and more data. Okay, so that's called pre-aggregation, and based on that, I created another collection, which I call Protein Archive. This just has the the protein information, the ensemble ID, and it has a list of peptides with the amino acid sequence, start and stop positions, and the count attribute. So every time I observe this particular peptide, I would just increment the count of this peptide in this particular document. Okay, so next time when I do this top 5 peptides for a specific protein, it is just like a lookup. Okay, so these are the kinds of things that you would have to think about when you develop applications which are database driven or data driven. So you need to figure out in advance what things you would try to access and then try to optimize those things. Okay, so that's another design thing. Now let's talk about a different application, a little bit more complicated. So this is part of the slide that I showed earlier. So mass spectrometers usually operate in 2 different modes. One is called MS1 mode, the other is called MS2 mode, and they keep switching between the two. So in the MS1 mode, they basically look for intact peptides. They scan for intact peptide sequences. So each peak here is an intact peptide sequence. Okay. Now, one way to go about this is that so once you scan for this, the next step is to pull out the most abundant peptides and do an MS2 scan on those and generate a fragmentation ion spectrum for each of those. Okay, so this approach is called discovery proteomics. You don't care what you get, you just keep switching between this MS1 and MS2 mode and keep collecting all the abundant peaks that you get. And then you assemble the data later on, do analytics on top of it. So that's discovery mode. In targeted proteomics, you have a predetermined list of peptides that you wish to monitor or follow. Okay? And for each of those peptides, based on their mass to charge or retention time, you have some criteria. And for each of those peptides, you have a list of fragment ions that you wish to monitor, which you will use eventually to do the identification and quantification of proteins in the sample. Okay? So there are 2 important things to decide. One is which peptides to follow, and the other is which fragments of those peptides to follow. Okay? For the first part, which peptides to follow, usually a good choice is peptides which are commonly observed for those proteins. That means they should, every time you run the experiment, you should observe that peptide. Second is the uniqueness. So that peptide should not be so redundant that it's seen in like 100 proteins. Then you would not be able to sort of get accurate results. So it should be unique to that protein. Okay, so those are 2 criteria. In terms of fragment ions, we should observe abundant fragments. So in the MS2 stage, we should observe abundant fragments, and those fragments should show stable fragmentation patterns. It should not happen that sometimes they're very low in intensity, sometimes they're very high in intensity. They should have some stability in patterns. And that's how we can actually accurately determine determine the actual abundance of the protein in the end, the analytics part. So yeah, those are the 2 steps. So let's see how we would use our database or this archive of previously collected data to get some sense of which peptides and fragments to follow. Okay, so for a given list of proteins that we are interested in, we first obtain 5 most common unique peptides. Okay, that's our first step. We want unique peptides and most commonly observed peptides for those proteins. For each of those peptides, report 5 most intense and most stable fragment ions. Okay, so that's the second step. Now, first step is pretty straightforward based on the example that we saw earlier. Simple pre-aggregation or a simple query can give you which peptides are unique for a protein and whether they are observed a large number of times or not. But step 2 is a more complex aggregation, which is not available as a simple operator in the aggregation framework, simple summation, simple averages. It's more complicated than that. Okay? So that's where the MapReduce paradigm comes into picture. The MapReduce is a very generic paradigm for doing distributed processing. Okay? It is inspired by functional programming languages where you have this map and a reduce operation. Okay? So best way is to give you a simple example. Let's say we have this input as a list of 5 numbers, 1, 2, 3, 4, and 5. And our goal is to square root each element of this list and then sum up the final result. Okay? So map operation usually applies to every element of a list. The same function, it applies to every element of a list. Okay? So that's our square root function. So you'll apply it to 1, 2, 3, 4, and 5. And then a reduce function will apply to a list, but it will reduce that list to a single value. That's our summation function. Okay? So that's a simple idea behind map and a reduce operation. But these map and reduce functions need not be so simple. They can actually pack arbitrary complex logic. You can write your own map and reduce functions and do arbitrary complex things with it. Okay? So let's see how we will apply it to MongoDB and our data archive. Okay? So MapReduce, it's a native implementation within Mongo. This is the MapReduce command. We first give it the name of the collection that we want to apply MapReduce on. That's our match archive that has all the information about peptide and spectrum matches. We also provide it the 2 functions, map and reduce, which will do all the operations, all the computations, all the logic. Okay? And then there are some extra things. Out is a string. If you want to store the end result of the MapReduce operation back into your database, you can provide a string and it will do that. And the other important thing is a query. So if I don't have anything in the query argument, MapReduce will apply to the entire archive. This archive has 10 million documents right now. For other much larger databases, this could run into many billions or trillions of documents. So if you don't have any query operator, this might take a while to run. But if it is possible to sort of subset the data, you can provide it in a query, just like you query for other things in Mongo. Okay? So in our case, we want to find out the 5 most abundant peaks for the shortlisted set of peptides that we got in step 1. Okay? So 5 most abundant peaks for those peptides. So we can just run a simple query. Amino acid sequence should be in one of these. It should be one of these. So we can provide a list of amino acid sequences that we shortlist from step 1. And then we can provide a $in operator, and we can just query it. So this list of 10 million documents will narrow down to, let's say, 500,000 documents now. Okay? Now, each of these 500,000 documents will look like this. So it's a giant document. This has information about the peptide, information about the modifications, and these are the scoring algorithm results. And it has information about which fragment ions matched which peaks. But we're not interested in the entire set of information. We are interested in the amino acid sequence, and we are interested in which theoretical fragments of the amino acid sequence matched which observed peaks. So what fragment ion matches were observed, okay, and with what intensities. So also, so let's say we narrow down from our query to 500,000 documents. These 500 documents will correspond to the peptide sequence list that we gave. So let's say the first peptide had about 20,000 documents. So it had 20,000 matches in my database. Peptide 2 had, let's say, 30,000. Okay? So our goal is to find the 5 most abundant peaks for a peptide sequence. So we need to gather all those 20,000 observations or instances in order to get the final result. We can't just pick out 5 or 10. We need to look at all those 20,000 data points. Okay? So that's what we will do in our map function here. So just like we had a list of numbers here and we applied square root function, we have a list of documents here, which is about 500,000 now, and we apply this operation. So extract amino acid sequence and extract all the fragment matches and their intensities. So this is our logic which we will put in map function. Okay? Now, the map function will basically scan through all these 500,000 documents, and it will pull out this relevant piece of information from each of those documents. And it will emit a key and a value for each document. Now, key is the thing that we want to group on. So we want to find the 5 most abundant fragment ions for each peptide sequence. So our sequence is the grouping key. Okay? So that's what we have here. And the value would be, for that particular document, what were the fragment ion matches and their intensities. Okay? So once the map step is finished, we have a bunch of 500,000 key value pairs, where key is our amino acid sequence, and value is the fragment ion characteristics, fragment ion intensities. Okay? And like I said, the first peptide in our list, let's say it had 20,000 occurrences in our database. We need to group these 20,000 together to come to the final result. So that's what the shuffle and group operations would do, and that's handled by Mongo internally. At the end of shuffle and group, we will have a 1 key value pair for each amino acid sequence that we are interested in. And the value will be a list of fragment ion matches for each of the occurrences in the database. So for peptide 1, we'll have 20,000 such things. For peptide 2, we'll have 30,000, 40,000, as many as were observed. Okay, so that's the map, shuffle, and group. Now, once you have all the data grouped by amino acid sequence, then you apply the reduce function on each of these amino acid sequences. So it'll take the amino acid sequence as input, and it'll take its list of observations, fragment ion matches, and you can apply any kind of arbitrary logic. You can count the number of times each fragment is observed. You can find average peak intensities. You can generate a consensus spectrum out of it, and finally return amino acid sequence and the final output, which is our 5 most intense fragment ions. Okay, so that's how you would basically break down this complex computation into a series of steps. So our first step was to get this query. So get the first step is to get these 5 most common unique peptides for the protein of interest, and then do the MapReduce on each of those peptides to generate 5 most intense fragment ions. Okay. So I hope that gave you some idea about how we can break down computations, complex computations in MapReduce. So just to summarize, it's for analyzing such massive data sets, we definitely need to use databases. Leads to much faster processing. It also leads to standardization of data access and management, and leads to much cleaner, more maintainable and reusable code. It also leads to faster turnaround in terms of new applications. So this map and reduce will be just like 5 or 10 lines of code for doing this 5 most abundant fragment ions for each unique commonly observed peptide. So it's like 5 or 10 lines of program. So it's fast turnaround time. Relational databases have issues, which I talked about, particularly impedance mismatch and difficulty to run on clusters. And MongoDB offers several advantages in terms of flexibility of data storage. It has a full-featured query language. It seamlessly runs on clusters, and it offers powerful analytics tools, particularly the aggregation framework and MapReduce. So designing applications or designing data analytics using large, massive archives and using these databases, it basically requires a different thought process. So you need to first of all figure out how to represent your question of interest in terms of these query operators or these MapReduce operations or these aggregation operations, and sort of build a pipeline. Okay? So you need to understand what are the common data access patterns. Let's say top N query is an important query. Range query on the MZ scale is an important query. Filtering based on various criteria in mass to charge ratio, charge state, regular expression on peptide sequences, spectrum quality, scores. Filtering based on all these criteria is an important thing to do. Grouping based on peptides, proteins, disease status, these are important things to do. So once you figure these common data access patterns, then you need to optimize using tools which the databases provide. So particularly how you design your database, how you model different aggregates, how you represent them in the database, what kinds of indexes you build for faster querying and access, whether you want to pre-aggregate some of the things that are commonly queried for, And since all these applications are running on clusters, you also need to think about data movement across networks. So you need to optimize that, take that into account when you design your analytics workflow. So this is work in progress. I have used some pieces of mass spectrometry data, but there are a lot of other data points or a lot of other kinds of data in mass spectrometry that we can actually store in our database and do other kinds of analytics things. So that's one step. And then for most of the common applications, library searching, clustering of mass spectra, then all other kinds of common things, targeted analysis, we need to develop, first of all, identify all those data access patterns, optimize those, and also develop novel applications on top of it, and then develop a user-friendly API for people to actually use these databases and build applications on top of it. So there are some references here. These are the main books. So NoSQL Distill is a very brief book about the general NoSQL landscape. It talks about all different kinds of NoSQL databases. MongoDB Definitive Guide, MongoDB Applied Design Patterns talks about, so Definitive Guide has everything about MongoDB, but Design Patterns is particularly about how you design your data model depending upon what your application is. And MapReduce Application Design Patterns, Applied Design Patterns, talks about how you can break different types of computations, common types of computations into a MapReduce framework. And then, of course, it's a MongoDB manual. So that's pretty much it.
Any questions for Himanshu?
Sure. I'm not sure if this is a question more or a comment. You presented very powerful. I think nobody here will doubt how powerful this particular implementation of NoSQL is for querying complex data. However, if I'm first time sitting down and trying to figure out the types of data you're using, I think using middleware and backend as your primary interface for the user is very confusing. I'd rather be interested in having access to objects that are more natural to me. For example, if I'm interested in working with peaks, maybe peaks are some of the fundamental objects, or collection of peaks, or collection of things. So that are native to the particular programming language that I'm using this in. For example, if I'm in Python, I would be expecting things to be some sort of objects that you can iterate over, for example, if there are some sort of collections. So you mentioned that you're working on sort of user interfaces. Is that sort of something that you're thinking, creating more of a data representations that are user-friendly with the backend and middleware provided by MongoDB? Is that sort of the
Yes, sort of. So we haven't done much work in that direction, but so there are a couple of things. So one is that there is a huge effort in terms of standardization in the proteomics community. So all these different kinds of things that we observe in mass spectrometry data, there are sort of standards in terms of how you address these things, how you address each peak, how you address a mass spectrum. So our goal is eventually to incorporate all those standards in our application. Then have a user interface which will allow biomedical scientists to run simple kinds of operations if they're interested. So all the common kinds of things that people usually do, like library searching or construction of spectrum libraries or clustering of mass spectra. These are several different biomedical applications or informatics applications. There's several biomedical so research questions like what kinds of proteins have been. So we're thinking about how to sort of make it accessible to both biomedical scientists and also to bioinformaticians who might want to develop applications on top of this with using the standard nomenclature and standard objects which sort of people in this community are familiar with. So, but we haven't done much work in that direction yet. Is that what you were coming at? Or?
Yeah.
Is there any translation utilities like converting a MySQL, provided we have some kind of these information on how to link these?
There There are some utilities. I haven't used them myself, but the reference that I gave, the Mongo, I think, so there is one NoSQL distilled, and I think the definitive guide, they do have some stuff on migrating from one database to another database, and they have some information about that. I haven't done it myself, though. So, yeah.
Yeah, I'm wondering if you could just discuss what are the weaknesses of NoSQL databases in comparison to relational databases. And then also, if you could sort of just characterize what types of applications are better suited for relational databases versus NoSQL databases.
So the biggest advantage of NoSQL databases is they can scale to very, very large, massive data sets very easily without much effort. You would have to do, you'd have to put in much more effort to scale using a MySQL database and achieve the same kind of results. But if you have like very complex kinds of relationships, then different NoSQL databases will have like different sort of features to support that. For example, there's no concept of transactions in these databases. So if you have like a banking or financial kind of a thing, let's say you're moving data from one account to another account. It should not happen that you've removed data from, you've removed like money from your account, and before you put it in your other account, that operation fails because the server dies or something happens. So you can't have that kind of stuff. So those kinds of transactions that both extracting money from one account and putting in another account, that can be done as a transaction in relational databases. That concept does not exist. There is some limited transactional capability, but only within a single, oh, sorry.
Yeah, no, sorry. I was just saying that's a huge difference. So there's no transaction.
Only within
atomic transactions.
Atomic transactions, yes.
So there's no support for atomic transactions in these NoSQL.
No, there is atomic transactions, but atomic transactions within the aggregate. So the document structure that I showed, so you can have atomic transactions within that aggregate, but not across different collections or across different aggregates. So that's the difference.
Yeah.
Okay.
It's still serious.
Yes, for those kinds of applications it is serious, but for things like scientific data that you just want to sit and analyze, that I think transactions are not that critical for those kinds. And then, of course, you can do complex relationships like joins across different things. Even relational databases are not stellar at doing very complex joins with large databases. For those, you might want to prefer graph databases, which are designed to do just that. So I think those are some of the trade-offs, I believe.
So I guess you mentioned something that makes me think maybe you should spend a little bit more time now thinking about the front ends, because for things where transactions are critical, you may want to have a mechanism for switching your backend from MongoDB, for example, to relational database for the segments of the data where you need it. And there are systems where this is implemented, where you, for example, you have a front-end object that looks the same whether the actual data is stored in MySQL, on disk, in memory, it doesn't matter, and you can implement all sorts of methods for accessing this data and make it as efficient as possible.
Yes, so there is a movement towards that. Although NoSQL databases have challenged relational databases in terms of their authority for everything, but they don't claim to be superior in all use cases. So what you were talking about is called polyglot persistence. That means you're using multiple databases, the right tool for the right job. So there is a movement towards that, and people are using like whatever tool supports. Sometimes you just want to access data by a key. You don't want to do a lot of queries. So for those cases, key value stores are more appropriate rather than these document-oriented stores, because key value stores are blazingly fast and they can also distribute across clusters. So depending upon what your application is, you can definitely choose the tool for the job. Oh, and the other, I think there's another trade-off. So relational databases have this SQL querying system, which basically is the standard across all SQL systems, all relations. They take as input tables and they churn out and give the output in the form of tables or tuples or whatever, relations and tuples. Okay, so that's sort of useful if you have, let's say, many different applications which are interacting with the same database, because there are no issues with like what you want to access. You can just write an SQL query. But here, an important design issue is that design of the aggregate. You need to design your aggregate in such a way that your query is fast for the particular application. That structure may not be more appropriate for some other applications. So those trade-offs also. If you want it as an application database, then these are good choices. But if you want sort of like an integration database, integrating multiple applications, multiple users across different applications or teams, then probably a mix of two or something could work. So.
If there are no more questions, let's thank Himanshu again.